So, in the previous lecture on GPU programming and architecture, we have been discussing on in order execution of commands and different synchronization primitives. For example, we discussed how workgroups can be synchronized, how you can put in barriers inside a command queue, and then there was this idea of how you can use CL wait for events primitive, because with every enqueuing command you have an event return. That event will have different status messages, and this status you can have a CL wait for event function using which you can query the event status, and unless a specific event reaches a specific status, you can also wait at those points. And you also have these primitives like CL finish and CL flush, which are also useful from that perspective. And now the next thing we want to discuss was that, well, even if you enqueue commands in a command queue, we usually assume that the commands will be issued to the underlying device for which the queue has been made in an in order fashion, which is not true. It may also happen that you can, if you want, you can execute the commands out of order, and you let the runtime system decide exactly in which order the commands will be executed. So, just to give an example what we mean, suppose this is the command queue, and you have you have enqueued a read command, then a kernel launch command, kernel has been enqueued, and then you have let me just redraw this figure. So, suppose I am just drawing this graphically. So, you have CLNQ write buffer followed by kernel launch, then you have a read buffer command after this, then you launch another kernel k prime like that. So, this if you have a normal command queue which is to be executing in order, this is exactly the order in which the different commands will be launched to the underlying device, right. But if I want, I can give the command queue an out of order property. In that case, the runtime system will decide whom to launch when, and you may be wondering why somebody will want to do that, because the runtime system may often have certain units which are free, but the command which is sitting in front of the command pipeline may not be for those units, those compute units, but for somebody else, whereas there may be succeeding commands there who could have engaged the corresponding execution units. For example, there may be separate read write units and compute units. The compute unit is not free, but at the same time I could have enqueued a read I could have taken out a read operation from the queue, and in that way I could have achieved some parallelism in using the runtime system. But for that, the command queue should also be able to issue the commands in a out of order way. I am just trying to motivate how out of order execution from the command queue may give me better performance. So, the properties argument in this CL create command queue with properties has to be set to an in order, an out of order or an out of order flag, in order to specify what should be the execution order of commands from the command queue. In out of order execution mode, there is no guarantee that the enqueued commands will finish execution in the order they are queued, as we have been discussing. And so, the takeaway from this would be that this is primarily being done by setting the CL create command queue with properties command while setting up the command queue itself. So, we will see if we are talking about in order execution of kernels, then the CL queue out of order exec mode enable property of any command queue is not set, and the commands enqueued are executed in order. Consider an example. This is the normal in order execution of kernels we are talking about first. If an application calls CL enqueue ND range kernel to execute some kernel A, followed by another call to CL enqueue ND range to execute a kernel B. So, you have enqueued two kernel launches A and B. The application may assume that kernel A finishes first and then kernel B is executed. That is the assumption from the application side. If the memory objects to be output by A are inputs to kernel B, then B will see correct data in the memory object produced by execution of A, because in an in order execution A will finish and then B will start executing. But in case it is an out of order execution, you do not have such a guarantee that A will finish before B starts execution. So, that is the problem, right. If it is out of order, as we said, if I make it out of order, then I lose such guarantee but then again I will like to sometimes make things out of order so that the runtime system can give me better performance if possible. So here we have a sample code of in-order execution. So there are certain parts which are commented because we are just training what are the functionalities you have to do there, and those functionalities are things that we have already discussed earlier. So consider that you have already set up the platform context and created the required read and write buffers, and you have created the queue leaving parameters as default so that the queue is an in-order queue. So the command queue is already there. So this is something we are doing here, and this comment is saying that you have already performed the setup of platform context and buffers and all that, and this is the command through which you are creating the command queue for a device which has been already discovered, and the device ID is stored in this device. The device belongs to this context which has also been defined, and other parameters are being set to default to maintain that this is the in-order queue. So you enqueue a write buffer command, you enqueue another write buffer command. So essentially you will be copying this buffer A and buffer B, right? You are enqueuing commands for that in the command queue. Then you will have suitable commands for setting kernel arguments. Once the kernel arguments are set, you will set the global and local work sizes as is usual in the OpenCL host program, and then you enderange clenq enderange on one of the kernels. So let's say it's kernel the first kernel in the queue, right, with respect to its global and local work size, and then you perform a blocking read back to synchronize. So essentially I am just trying to say that after this command you have a clenq read buffer command for the same queue where you are going to read back the outputs of the kernel, right, and while having that read buffer command you set the blocking read property to true, so that unless this command executes the host program will not go forward to the next command. So here you are achieving synchronization using the blocking read, right. The blocking read is ensuring that you don't go beyond to the next kernel's read buffer commands unless this happens, right. So after that you again you may have read buffers performed here, clenq read buffer like this, and then again a clenq read buffer. So these are the blocking reads you are performing, right, once this kernel has executed, and after that you have the cl finish command. Now the cl finish command will again ensure that inside this queue whatever commands have been enqueued have all finished. So of course the blocking read will, these blocking reads, if they are blocking reads, then anyway you cannot go beyond each of them, and this additionally says that well you can go beyond this point only when all these commands are finished. So this is the way you will ideally write the program in case you have a simple in order code. So just to summarize, like you have a normal in order execution of kernel. The application can assume that kernel A finishes first and then kernel B is executing, just as we have discussed, and the memory objects which are output by kernel A are inputs to B, and then B will see the correct data in objects produced by the execution of A. So if I want a normal in order execution, so what will I do is after A has finished, let's say I am having a blocking read, and then if required I will again do a blocking write. So in that way I can synchronize to the host program, or here I am performing a blocking read back to synchronize from the buffer outs. And then let's come to the other option, which would be this out of order execution of kernels. So for out of order execution of kernels, you will have this clq out of order exec mode enable property of the command queue set at the right at the time when you are creating the command queue, right. So in that time the commands enqueued in the command queue may execute out of order. So out of order, as we have discussed earlier, that you don't have any guarantee that the enqueue commands will finish execution in the order they are queued, right. So because they will start executing out of the order. It is possible that an earlier ND range kernel call to execute kernel A identified by some event A may execute and or finish. So later then a CLNQ ND range kernel to execute some kernel B, which is called by an application at a later point of time. So it may happen that whatever commands you have enqueued there, they are executing outside that normal order in which they have been enqueued. So maybe you have enqueued, you have executed these two commands, CLNQ ND range kernel for a kernel A, and again CLNQ ND range kernel for a kernel B, but the kernel B gets actually launched to the device before kernel A has been launched, or kernel A has been launched but it is still not finished. Just to go back, why this issue was not there in order execution, primarily for this blocking read. So suppose you have a code where you have copied, you have written two buffers again to the device memory, and you have executed a kernel which would have worked on the buffers A and B, and then you are reading the buffers, performing a blocking read back to synchronize. Okay. So if you have done it in such a way, so this is a blocking read, as you can see, and then so that is actually ensuring that the kernel finishes, and after that if you launch another kernel, it's okay, right? But so if you have an out of order property enabled, then you have to actually keep in mind that the kernels may get launched in a different order, although you have enqueued them in order, but they can technically get launched, because again I will just try to remind you, this program is what it's doing is it's just saying what is the order in which I am enqueuing the kernel. Here one kernel is enqueued, maybe at some point I am going to enqueue another kernel. The host program is executing commands in this sequence, right? So this is just the sequence in which the host program is executing. Inside the command queue, all these write buffers, kernel, again the read, these are all commands that are getting enqueued in the command queue. So this is the execution order of the host program, right? This is the execution order of the host program. But when I have in order execution from the command queue, then these commands are submitted to the device exactly in this order. Only in that case I have execution in order. Otherwise, if I have an out of order setting in the command queue, then just by enqueuing them in order through the host program, I don't have a guarantee, because still in that case you see maybe I am performing a blocking read, but doesn't matter. This ND range kernel has been enqueued here, right? It doesn't mean it is being issued to the device or it has started execution, it will finish and then K2 will start, right? Here, by performing the blocking read or by the CL finish, all that we are doing is that we are delaying the enqueuing of the second kernel in the command queue, right? Because we have a guarantee that we have the execution will be in this order, right? But if the command queue is set in an out of order, and if I am not having this sequence of commands to be executed, I may not have such a guarantee. So we will see that what happens in that case. So to guarantee a specific order of execution of kernels, this following can be done. So you may wait on an event A by specifying the event in the event list argument to the CLNQ ND range kernel for kernel B. So for every kernel, I can have an event wait list that only when those events assume a specific value, then the kernel will execute. So I can have the other option would be that I put in a marker or a barrier using the CLNQ marker with wait list or CLNQ barrier with wait list. So this, as we have seen, that I can enqueue barrier or marker commands in the command queue. If I put in such markers, then they will also ensure synchronization inside the command queue and prevent some out of order executions scenarios which I would want to avoid. Those which I want to happen to enhance performance, those I can keep, but those that I want to avoid, that I can enforce by suitably positioning the markers or the barriers in the comment queues. This ensures that previously enqueued comments identified by the list of events to wait for have finished, or all previous comments, I would say. Now, the other way would be, as we have discussed, that I can have a callback function registered, and I can have CL set event callback, so that when the execution status of a comment associated with an event changes to a given status, then this function would actually let the system know, and I can make some progress forward, right. So, whatever synchronization primitives we have discussed earlier, they may also be used to actually provide sequencing inside comment queue in case the comment queue is already set for out of order execution. So, again I will just repeat, if you have in order execution property for the comment queue, that is fine. So, comments will be getting executed in the sequence, and so I don't then I don't have a problem, because you have writes followed by one kernel executing, then you can have a blocking read. So, unless that read is finished, your host program doesn't go to the next enqueuing operation, right. So, and there is also one point we will need to say, that suppose I was not having a blocking read here, then what happens? Well, the host program is following this sequence, it will enqueue the read buffer command, then it will also enqueue the, let us say you are also enqueuing the next kernel for executing. So, again the host program is just enqueuing, right. So, it is not waiting for the read command to complete before it will possibly enqueue the next kernel after at any of these points, right. Now, due to that, even before all the reads happening to an input buffer for the next kernel, the kernel may get launched. So, that is why, to avoid that, you will like to have the read set to a blocking read property, fine. So, in that way, in this code, as you can see, we will have this blocking read, and then the blocking read would be followed by another ND range kernel command for the next kernel, right. So, this is about the in order execution, and then just to summarize, in the out of order execution you have a lot of problems, because unlike the in order execution, where the comments you are enqueuing in the order in which the host program is executing, and the actual execution and actual launch of comments are going to follow that exact sequence, that gets broken, right. Because in the out of order execution, although your host program will move like this and enqueue comments in a specific order, the comments may actually start executing in a different order, because it is an out of order execution. So, this is something again I will keep on repeating. I am enqueuing comments in order here. Since I am enqueuing comments in the order here, and the command queue is set to in order execution, the comments will also be launched in order. But here also you have to be very careful. Again I am repeating, I know, but this is important. I have to be careful, because I am launching the comments, I am enqueuing them in order. So, that will ensure the comments get launched in that order, but still it does not ensure that the previous command finishes before the second command executes, because they are getting launched in the order, right. For example, as I said, this read followed by the next kernel launch, there is a reason why I make the read a blocking read, so that the data is available for the kernel launch even in case of in order execution. But as you can understand, the problem is far more pronounced in case of out of order execution, because the host program is enqueuing in an order, but even though you are enqueuing in an order, your comments may not be submitted for execution in that specific order. And so, even in order execution we had that issue, right, that you may, yes, you may be submitting them for execution in a specific order, but you are not waiting for previously issued comments to finish. here the issue is even more grave, I would say, because first of all you are not even submitting commands for execution in the host specified order, and again so you are submitting them in some order that the runtime system wants apart from the order in which the host has enqueued. Moreover, the order in which they start execution may not be same as the order in which they finish execution. So that would mean this kind of a bad scenario. In a worst case, I would say, let us say the host has enqueued commands in an order. With in order, I had already have a problem that without, let us say this is first execution, this is second issue, this is first issue, but the second, if the second issued command has a dependency on the first command, for example a read event has to be completed before a kernel has to execute, then I have to either put in a blocking call, or I have to put in a barrier, or I have to put in some other synchronization primitive, all that. So that's already the problem in order. Now you have the additional problem that actually although you may have the first command followed by the second command, when they are getting issued, maybe the second command has been issued followed by the first command has been issued, and that is actually followed by the third command that has been issued, and maybe the second command has a dependency on the first command. So the second has been issued, first has been issued, third has been issued, right, this time, and the second has a dependency on the first, that is also not specified. So you may have multiple issues, right, because the second having a dependency on first was already the problem in order. For that you have to choose to use blocking and all that. Here you are further complicating the problem with this out of order execution, because you have to somehow make the system know that 2 has to depend on 1 and all that. So how to ensure this? As we have discussed, that we will be making use of event wait lists, we will be making use of markers and barriers, and we will be making use of callback functions. So let's see what are these. So OpenCL will first of all let's consider that we have already set up the platform context queue and the buffers are created as usual practice, and you have some OpenCL events defined as write event A, write event B, and you have an event defined for kernel event, you have an event for read event and all that. Now we will start creating this normal enqueue commands, and we will be specifying some events to be attached to them, which we were not doing earlier. So let's say we have a write buffer command. So the write buffer command in a defined command queue, you are writing the buffer, you are enqueuing a command to write the buffer A into a device, for the specific device to which the command queue is attached. You have blocking rights, and you have the size and other specifications, and you attach a command an event write event A with this, so that the status of this command can be found from the status of this write event A OpenCL event. Similarly, you also attach the write event B for the other write buffer command for buffer B. So you have enqueued 2 write commands in the command queue. They are writing in the device memory buffer A and buffer B. The status of these writes can be known from the value that the runtime system will assign to write event A and write event B events. After this, you have usual definition of kernel arguments, you have usual definition of local and global work sizes, and now let us say you create an event list by packing these 2 events, write event A and write event B, into this array event list. Now why would you want to do that? You want the kernel enqueuing to happen depending on whether these 2 write events have been have actually completed. So what you do is now you enqueue the kernel for execution in the command queue, provide its parameter settings, global and local work sizes, and you also give it an event list to wait on, and you attach with this command the kernel event. So if I try to draw a graphical picture here, what's happening? This is the queue. So you have executed you have enqueued a write buff command, you have another write buff command, and you have enqueued a kernel with this write buffer command. So these are the two write buffer commands I am talking about. These have been enqueued, right? Now with these two, you have attached two events, OpenCL events, and those two events now start appearing into the event list of this kernel. What are those OpenCL events? Write event A and write event B. So these are the OpenCL events. Write event A and similarly B, and they are here in the event list A comma B. So now you don't have the problem, right? Because the event list is something like only when these events are finished, they reach their CL finish, only then this command which have been enqueued can execute. Okay. So now even if the command queue the runtime system try to optimize the execution of the command queue, even if it tries to initiate dispatch of this kernel before this, it cannot, because now you have explicitly specified the dependency of this write event A and write event B. Sorry, this should be write event A and this is B. You have explicitly specified the dependency of write event A and write event B with the execution of the kernel using these signals or the OpenCL events write event A and write event B. So now when these two are done, they actually force that even this cannot execute out of order. It can only execute after write event A and write event B are done and they reach the status of CL finish. Now when they are done, you see this ndrange kernel command, when you are enqueuing this in the queue, in the last argument you have the kernel event. So that's another, the last flag, that would mean that with this command itself you are attaching another event called kernel event. So that means with write event A and write event B finishing, they can start in any order, right? I have not given any order, it can is an out of order queue. These two can start in any order. When they finish, only then the kernel execution can start, which is being forced by this event list here. When the kernel execution ends, then you have also associated this kernel event type OpenCL event, kernel event, with the queuing of this ndrange kernel, the queuing of this kernel. So now only when the kernel execution finishes, then this kernel event will get the finished status, and this can be used for upstream further execution, which are dependent on the kernel's execution. So for example, after this point you don't have any importance of write event A and write event B, so you can just release those events, right? So you do a CL release event, that's an OpenCL API function. Now you want the second kernel to execute, right? So when do you you want to read the output that has been computed by this kernel. So for that you have you will enqueue a read operation. So now you will enqueue a read operation, right? So you have a read operation. Now this read operation is waiting for this kernel event, and this read operation will output a read event. So that is the associated. So maybe we will say that it is waiting for the kernel event and it is associated with this read event, right? So when this read operation is enqueued, it is restricted from starting earlier by its dependency on the kernel event, right? This is the dependency on the kernel event. Only when this is done, then read operation can start. When read operation ends, the associated read event will be true. At this point you don't have any requirement of the kernel event, so you can release that event, and you can actually use this read event to have some further dependent executions going on here, right? If you want them, you can enqueue more comments with the dependency of this. So here, if you want to block until the read has completed, your option would be you use the function CL to wait for events, unless you don't want to enqueue another command which will depend on the read event. You just wait for this event using the CL wait for events, right? So you just wait here. So the option we choose here is we are not enqueuing any more command. So you are just waiting, and then when it is done, then this function is blocking the execution here. It will let the execution progress, and then you release everything. So here we are showing that how using these events and dependency lists of every enqueue range command. So this enqueue commands, earlier we have been just enqueuing commands into the queue, but now you are showing how enqueue can be done with dependency lists. The last two arguments of every enqueue command are used for this event dependency list. The last argument is for the output dependency, that well, this is done, this event will now go on. So this is actually specifying the event that you are attaching with the command that we have enqueued, and this event status will keep on changing with the different execution status of this command. And before this event, the last but one argument is the event list. This event list may contain a set of events, and when all those events actually get the CL finish, then only this command can start executing. So this is how you can mark out dependencies and force an ordering. Now there could have been another approach, which is that you suppose you have this CL enqueue ND kernel. So you enqueue the kernel, you have the event list, and you have the kernel event. So we are now speaking from that point. Now the read will wait on the kernel completion to run. After that, you use this kernel event to enqueue as a dependency to enqueue the read event. When the read event is done, you get the read event call. So the read event status will turn CL complete, right? Here also you had the read event. Up to this is fine. After that, you are doing a wait for events. Instead of wait for events, alternatively, what you could have done is that you could have used the callback function. So this is the other approach we sought, right? So what the callback function will do is, it is indicating that callback function will be registered with this event using this CL set event callback primitive. So all you do is, with this event CL read event, with this event read event, you are associating a function called callback function. So the way to read it would be, when this read event will get the status CL complete, then this this callback function will execute asynchronously, okay, with some arguments. So the definition of the function prototype CL event callback is that this is the event to whom you can look that whether this event has attained this execution status. When some event, like in this case the read event, has attained an execution status, in this case CL complete, then some callback function like this of type CL callback, in this case we are just calling the callback function name as callback function, will execute with some argument which can be specified here, right? Now so in that way I can have another callback function to execute, and finally I would just release the read event that we have defined earlier, right? So that can be another way to synchronize things in the out of order execution. So this is a picture we have taken from this reference, which we have attached later on. Is the OpenCL, it's a nice book on OpenCL and OpenCL 2.0 I would say. So as you can see that we have these write buffer comments, and these are the associated events that we have defined. The ND range kernel is the enqueued kernel. Here it's enqueuing this enqueue ND range kernel is enqueuing this kernel. It can only execute when these events are done, and it will output the kernel event to CL complete. And using this kernel event, I can initiate the execution of read buffer, and when this read buffer is done, I will get as output the read event, and in that way I have the data synchronized with the host. So this is the other option of dependency. Apart from this, we have an option of profiling operations on memory objects and kernels in OpenCL. Like so, the way it works is you can profile OpenCL. I mean, yeah, in case you want to profile the execution of an OpenCL program, you have to set a command queue with CL queue profiling enable flag. Now, once that is done, then the event objects that are created in the queue from enqueuing of a command, they will, I mean, they can also store a timestamp for each of their state transitions. So, just to remember, with every command that you enqueue, you can have an associated event object. For that event object, you can have, as we know that the runtime will keep on changing the status of that event object, right. Now, as we have discussed earlier, that every enqueue command will return an event, right. Now, if you actually give a name in that field of enqueuing of CL enqueue commands, then for a specific event, then that returned event would be in the name in that event, right. And so, you can use that event name to sample the different possible status like CL complete, CL finished, CL submitted, CL pending, like that, to know what is the status of that command. Now, with profiling enabled, the system will also can also give you a timestamp when the status changes from something to something. Okay. So, for this you can use the OpenCL API CL get event profiling info. So, this is given by a 64-bit value that describes the current device time counter in a nanosecond resolution, that you can get to know when some event can attains a specific status. Let us take an example. Suppose you have created a command queue and it is in profiling enabled mode. Now, you are enqueuing a kernel in that queue, and that kernel has a event list, and you are attaching an exec event with that kernel. Now, so essentially this would help you. I mean, since you have the queue with profiling enabled mode, so the runtime system will ensure that for this exec event, during the lifetime of this event, whenever it is switching these different modes, the corresponding timestamps are collected by the runtime system, and you can use profiling information API to collect those values. So, you can use this CL get event profiling info function to get those values, and so what we can do is give the current time count device time counter in nanoseconds. So, that is what it does. I mean, it will sample it out. When the command identifies the event is enqueued, submitted in command queue by the host, and starts and finish execution on the device. So, these are the different states through which the command will go through, and all those states, whenever those states are reached, those values can be collected. For example, you can use this CL get event profiling info API for this exec event and see that so this is the way you have to do it. So, for this you have to write it like exec event, this is the event, and CL profiling command queued. So, essentially this would return what is the exact time when this exec event reached the status that it has got actually queued, what is the exact time when it has been submitted for execution, what is the exact time when it starts execution, and what is the time when the command is sent. So, these are the different statuses that can be sampled, and when these statuses are sampled, they would actually get returned in this. So, this is basically the time. So, CL profiling command end. So, you have queuing time, submitting time, submission for execution to the device, start time for execution, actual execution, and the end time for the execution, and all these values get stored in this in these corresponding addresses for queued, submit, start, and end, as we have been defining here. So, it is this field, right. It is this field, parameter value field, in which those values get stored, right. And finally, if you want to print them, you can just use this a normal printf function and print the exact timings for that specific kernel getting queued, the kernel getting submitted, the kernel execution starting, and the kernel execution finishing, because all of them have got stored in these variables. So, these are some important references we would like to you may want to visit for knowing in more detail about OpenCL. So we have made exhaustive use of these two resources. The first one is the OpenCL specification made by Kernels, OpenCL working group Kernels, which is freely available in the internet. The second one is a very nice book on heterogeneous computing with OpenCL by these authors as written here. So I hope this was a nice journey through the basics of OpenCL. Thank you for your attention.